let's look at using the inverse matrix to actually solve a system. And let's also get the general method for finding an inverse, not just for a 2 by 2, but for any size. We are mostly just getting comfortable with computations in section 2.2. 2.3 is going to give us the theory behind inverses. But we'll just get a couple little theorems right here. But let's start with our example. So we have this little system of equations, which obviously we could solve with row reduction, but our point here is to learn the inverse. So first of all, this is linear algebra, people. Come on, let's put this in linear algebra form. So 2, -5, 1, 4 times xy equals 3, 5. This is the matrix equation. This is what we typically call an A times an unknown vector x. This should result in our known vector b. And our method here, instead of creating an augmented system, is to find the inverse. And once we find the inverse, we'll multiply both sides of our equation on the left, because matrix multiplication is not commutative. Multiply both sides on the left by the inverse, and we know that the A inverse in A will reduce to the identity, and the identity times x is just x. So this solves for x. So really, once we find the inverse, all we need to do is multiply the inverse on the left by b. And that will give us our solution to our system of equations. So it's worth pointing out here that if there is an inverse, that means there's only one solution to the system. Think about that for a second, right? We've got sort of three possibilities. We've got, in general, that there's either no solutions to a system, or there's a single solution, or there's a free variable and there's infinitely many solutions. And if we can find the inverse, we know that it's got to be this one, that there's just one solution. It's not 0 because we can compute it, A inverse times B, and it's not infinitely many because A inverse times B is just numbers being multiplied by other numbers. It just produces one answer. So that's a theorem that's worth mentioning here. It's in the book, Theorem 5. It just says if A is invertible, then for each B, not just 3, 5, but 107 and a billion negative 2, for each B in the appropriate space, R2 for us, for each B, the equation AX equals B has a unique solution, and this is how you find it. The unique solution is A inverse times B. I'm going to add on to this theorem a little bit. I'm going to go a little bit beyond, well, I'm going to bridge Theorem 5 to Theorem 7 is what I'm trying to do here. Spoiler alert. If I had taken this system and tried to solve it with row reduction, which would have worked just fine, see, it would have looked something like 2, -5, 1, 4, 3, 5 on the end. And assuming the matrix has an inverse, which it does for this problem, I'll just spoil that for you too. Assuming it has an inverse, that means there's a unique solution. Just one solution, which means there's got to be two pivots. Right? No free variables. So it means when you row reduce, you've got to get it all the way down to, and then whatever the solution actually is. There'll be numbers over here. But that means that the part that came from, or the part that was A, should be reducible to I, to the identity. Because that's how it solves when you just have a single solution, right? It looks like that for a square matrix, which is what we're working with. So yeah, let me just point out Theorem 7, and this will give us our technique. So theorem 7 says if a square n by n, 2 by 2 for us, matrix is invertible, or it is invertible, if and only if A will row reduce to the identity of the right size, I2 for us. And the sequence of row operations that reduces A to the identity, so whatever it takes to go from 2, negative 5, 1, 4 to the identity, is also what will turn the identity into the inverse, which gives us a way of finding the inverse. It's saying whatever you have to do to A to get it to I is the very same thing that would turn I into the inverse. And that's a little bit, let me, by way of analogy, take you all the way back to our example from the last video, where I was using this to start us off. And it's pretty easy to look at that and say the inverse of 5 is 1/5. But suppose you didn't know that the inverse of 5 was 1/5. You'd say, well, what does it take to turn 5, which is like our A in this problem, what does it take to turn 5 into the identity, into 1? Now, say what I would have to do to turn A into the identity, what I'd have to do to turn 5 into 1 is I'd have to do 5 divided by 5, which produces 1. And the claim here in this theorem 7 is that those very same step in this case, dividing by 5, that very same step would also, if you started with 1, if you started with the identity, dividing by 5 would produce the inverse of 5. I know this is almost too trivial, but it is too trivial for numbers. It's not too trivial when we're talking about matrices. So the step that would turn your A into 1 is the same step that will turn 1 into A inverse. So the algorithm here says, let's just go ahead and do the steps to both things at the same time. So it says augment A to negative 5, 1, 4 with the identity, and then row reduce. And the form of AI, as you reduce A and get it down to I, those same steps will also be happening to I, and they'll turn I into A inverse. Okay, I know that's a lot of talk. Let's look at how it actually works. Yeah, I almost said any questions, but I'm so used to being in the classroom for this. So any questions? No? Okay, we'll go on. Okay, so let's try this method here. Let's find A inverse by saying 2, negative 5, 1, 4, augmented with the identity, 1, 0, 0, 1. So that's our AI, which we are hopefully eventually going to be able to reduce to I and A inverse. Okay, so let's just start doing row reduction. So the first step would be to put a 0 in the bottom left corner, so that'll be negative 1/2 of row 1 plus row 2 becomes the new row 2. So that would be 0 right there. Let's see, that would be 5/2 plus 8/2 be 13/2. Negative 1/2 plus 0 is negative 1/2, and 0 plus 1 is still 1. Okay, I've got a 0 on the bottom left. I'm going to go ahead and put a 1 where the 13/2 is. So that would be, what, 2/13 times row 2 will become the new row 2. So 2/13, so that'd be 1. Let's see, 2/13, the 2's cancel, so that would be negative 1/13, and 2/13 times 1 is 2/13. I need to put a 0 where the negative 5 is, so that will be 5 of row 2. Added to row 1 will become my new row 1. I'll squeeze one more step in here down on the bottom, and then we'll take it home over here on the right. Okay, let's see, 5 of row 2, so added row 1, so 2, 5 added negative 5 is 0. That'd be negative 5/13 plus 13/13, so 8/13. And 5 of that, so 10/13 added to 0, so 10/13. And then the last thing I need to do is put a 1 where the 2 is. So that would just be multiply the first row by 1/2. So first row times 1/2. 1, 0, half of 8/13 is 4/13. And half of 10/13 is 5/13. And 0, 1, negative 1/13, 2/13. And I think I said in the last video that inverses often involve fractions, which is definitely the case here. And you can certainly see why most of the time to find an inverse we will use a calculator. Right, in 2.2 I want you to practice it by hand. That's why there's only 4 homework problems assigned. But beyond 2.2, anytime we find an inverse, we'll use a calculator to find it. And any matrix calculator can find an inverse. If you have a calculator that only does decimals, obviously the decimal output is not the preferred form here. It's ugly, plus those are rounded off. They're not even the exact right values. So make sure that your calculator can spit out a fraction form for you as well. Okay, all that to say that we have found the inverse. It's this chunk right here. And to get the solution to our system, we just need A inverse times B. So we just need to multiply 4/13, 5/13, negative 1/13, and 2/13. Times 3, 5. And let's see, I'm going to say that'll be 3 of the first column plus 5 of the second column, and I'm really going to stretch. Don't do this the way I'm doing it, but I'm going to stretch. I'm going to try to do this all in one fell swoop here at the end. So 3 times 4/13 would be 12/13, 12, and then 25/13. So 12 and 25 is 37/13. And for the bottom, it'd be negative 3/13 plus 10/13, so 7/13. So that should be the solution. We could certainly check it back in the original equation, or you could check it just by doing a matrix multiplication with your matrix calculator and make sure that this is what comes out. And maybe I'll just actually check it that way. Just check my multiplication here since I'm not super confident. So we wanted the inverse times, I want to insert a 2 by 1 matrix, which was 3, 5. And it is 37 thirteenths and 7 thirteenths. Okay, good. My multiplication arithmetic skills are still okay. I guess I can keep my job. So yeah, that's it for 2.2. Again, just 4 questions in the homework, 2 that ask you to find the inverse, and 2 that ask you to solve a system. And again, I'm making it short because I would like you to practice finding these inverses by hand. So do that for tonight. Starting in 2.3, we'll get some theory about inverses, and we'll let the calculator do the groundwork from that point onward.